Hello everyone, I got certain confusions. Am I audible or not? Hello everyone, am I audible? Can you please confirm me in the chat window, am I audible or not? Okay, hello everyone. Okay, let me start the session now. Okay, so let me tell you about the binary search and linear search, how it will work on the different computer. Like we are taking the computer 1 and linear search, we are taking the computer 1, that is the fast computer, and computer 2, that is the slow computer. Okay, and again let me open the new window. Computer 1 and computer 2. Computer 1 is the fast and this is the slow. And here I am executing the linear search, and here I am executing binary search. Okay, so in the starting, my linear search, obviously it's executing on the fast system, so it will take the less time. And binary search is executing on the slow computer, so it will take the more time. But when I increase my input is increasing. If you will increase your input, obviously at certain time your linear search will slow and your binary search will be fast. If you have data, that is the sorted data. Okay, so what the conclusion here, if a algorithm that is asymptotically fast, if I'll run this algorithm over a slow computer, then also it will run fast. It will take less time when we increase the input. Are you getting the things? Linear search always takes order n time, and your binary search always takes log n time. We will see how it's calculating, how we are calculating the time. Here you can just consider linear search is taking order of n time and your binary search is taking order of log n time, and we are taking here the worst case. It's not the best case. Worst case, when we want to search an item and that item is not at the first place, or you can say that item is in the last place. So what we will do, we can search by two ways. One is the linear search, another one is the binary search. In the linear search, it will take less time in the starting because it's executing over the first computer. You can execute this on the GPU. But in the when you increase the input, obviously at the certain time your linear search will go slow and your binary search will go fast because its complexity is order n. When you increase the value of n is 10 to power 9, then order of n 10 to power 9 is more than the log of 10 to power 9. Okay guys, so this is the way how to select a particular algorithm and which algorithm is best. Now the question comes to mind is, asymptotic analysis is always works. Here what we are doing, we are keeping only the variable terms, like there is 2n plus c and 4n plus n. In this case, in the case of asymptotic notation, we are taking care of only the variables. We are avoiding these constants, these 4 and 2. If it is the log n, 2 log n, and if it is something 200 log n, 2000 log n, we are taking care of only the log n. We are not considering these constants. Here we are taking only the fastest growing term. Like in this algorithm function, f of n is equal to 2n plus c, fastest growing term is n. So we are keeping only the fastest growing term and we are avoiding drop the constants. Okay, and we are dropping the constants. Okay, so this is the linear function, simple linear function. So you can conclude we cannot measure the time complexity and time to execute a particular program in absolute term, like in the terms of time. We can calculate that time in the form of a mathematical way. And in this mathematical way, we are taking the different notation. This is the bigger notation. Okay, so asymptotic notation is always works when we are changing the input, when we are increasing the input. With respect to the input value, we are calculating the asymptotic notation. Are you getting the things? Can you just confirm me in the chat window? It's a little bit tricky topic, but you have to understand these things. Okay? So basically, now what we will do, we will run a program. We will create a program. Pratyush is asking a question, ma'am, I cannot get it. Why linear search takes less time if it traverses each element? Just consider one case. Here I have considered two cases. First case is I'm taking a fast computer and linear search I'm performing over a fast computer and binary search I'm performing over a slow computer. So initially your linear search is performed over the fast computer, then it will take the less time. But when input value is increasing, then our linear is always take the more time because its a complexity is order of n. Are you getting the things? Now I think it should be clear to you. So let me conclude till now what I have told you. I have told you two things. What is the performance measure? For the performance measure, we need to take care of scaling. We need to take care of if software is feasible or not feasible, and we need to take care of speed of the software. And for that performance, we need asymptotic notations. Like we just want to calculate the time and space. We cannot calculate for the algorithm because it depends on the hardware also. So we will go with the asymptotic notations, and asymptotic notations basically used to represent the taking time to execute a program in the form of mathematical way. There are the different notation, and it's basically depends on the input size. We don't measure the actual running time. We measure according to the input. If our input will increase, initially I have 10 values, and when I increase the values to the millions, then how it will work, how my algorithm will perform. We calculate the time and space taken by algorithm increases with the input size. This is the important point. And usually asymptotic notations we represent in different forms. It falls under three categories. One is the average case, best case, and worst case. What is the average case, best case, and worst case? It is just like you can relate this with your life also. Like best case, minimum time required for the program execution. Suppose in the linear search, I just want to search the element that is present at the first position. Okay? Sometimes we are lucky enough in the life, like exams cancelled when you were not prepared. You can take the example of COVID-19. You guys were not prepared for the exams, and exams are cancelled. Okay? And sometimes what happened? A surprise test when you were prepared. So this is the best case, but it never happens. You can say it is a bogus. It rarely happens. Okay? And second thing is worst case. Maximum time required for the program execution. A program is taking maximum time. Sometimes we are unlucky. Questions you never prepared asked in the exam. Or you can say you are going somewhere for the walking, or somewhere for the playing. That time maybe there is rain. So these are the worst cases. Similarly, if I'll search for an element in a list, and that is either that is not present in the list, or either that is the last element. So for that, in the linear search, what I need to do, I need to traverse the complete list. Okay? So this is the worst case and best case we know. So in terms of time, how much iterations, how much time an algorithm takes, we will calculate in the practical. And average case is okay. Overall, the life remains balanced with a mixture of lucky and unlucky times. Okay? So we will calculate the average time required by the program execution. So how to represent these average case, best case, and worst case? In the mathematical way, there are the certain notations like big O notation, omega notation, theta notation, and little o notation. Generally, we are using big O notation. Big O notation basically used for the worst case complexity, and for an algorithm, we always assume worst case. Like we assume that we are always unlucky. Never things happen in favor of us. Okay? So we consider the worst case. Big O notation represents the upper bound of the running time of the algorithm. How much maximum time it will take. It gives the worst case complexity. And these are the mathematical formula. I'll explain you later on. Don't worry about it. Okay? Right now you can consider, like we know what is the best case, we know what is the worst case. So big O is used to measure the time complexity as well as the space complexity. So this is the important thing. When you you are going to learn the data structures, you have to make familiar with you have to make familiar with the bigger notations. There would be a question in interview about these notations, and certainly always people asking about the notation, like if you are doing this task using this algorithm and other algorithm, how these algorithms affect, which algorithm is fast and why. Okay, so bigger is useful for all programming language. It's not like it's only the Python, it's for Java, it's for C. These notations are useful for every programming language. Now what we will do here, like here, I'll open my Google Colab and I'll write a program. You guys can open your Google Colab. You know how to work with the Google Colab that we already covered yesterday. So just open your Google Colab and here we will write a simple program for the searching. Or you can say we just want to search a particular element, or we are taking a list. L is equal to a list of numbers, like I'm taking a list of numbers 2, 5, 6, 8. This is a simple list I'm taking. And here I'm defining a function. How to define a function in the Python? Def keyword I have to write. Def, and then I'm doing the square of the numbers. So get squared underscore numbers. And here I'm taking my list L, and inside this function I'll write certain statements. Square, I'm taking an empty list square numbers, and here I'm writing a loop for n in L square dot append n into n. It will return square. I'm getting the squared number of a list, and here I'll call my function get underscore squared underscore numbers. Data structure is not about the theory, you have to practice it. Obviously any programming language you have to practice. It's not about I'm telling you the things and you are listening only. You have to practice these things. This is the simple program I have written in the Python. I have taken a list L that have 4 elements, and then I have written a function def, and this function name you can give any name. What happened? List object has no attribute append. Okay. Oops, spelling mistake. This is the new list I'm getting. 2, 25, 36 and 64. Okay. So this is the output 4, 25, 36, 64. Are you getting the things? This is the simple Python program. I have not written anything. Now, if I talk about the time, here I have taken only the 4 numbers. Okay, I can calculate how much time a particular program is taking. I can calculate the time using the time module, import time. And then start time, I can record start time is equal to time function. Okay, and at the end I'll record the end time, end is equal to time, and then I can print time taken by the algorithm by program. It's a end minus start. And this is the milliseconds. Similarly, if I'll increase the input size, time will increase. You got a link for the registration form. So you guys who didn't fill their registration, and you need to fill this registration form. Here there are the certain columns. If you have registration number, you can fill the registration number, otherwise you can keep it empty. So guys who didn't get the registration number, we will provide them the registration number. Here you need to fill certain informations for your attendance, and mainly for the registration number. Some guys didn't get the registration number. So those who have registration number, already have registration number, please fill inside this, otherwise keep it empty. Okay. So what we are doing here, we are calculating the time. How to calculate time to taken by a program? Here is the time module inside the Python. L is equal to, we have taken. Now I can increase the list items, like simple items I'm increasing. And now I can run. You can see the difference. It is very less inputs I have increased. When I increase the inputs till the millions of number, billions of number, then difference is clear. You can see that by your eyes. Right now it's a little bit difference, but you cannot view the properly. Okay, so this is the algorithm. How much time this algorithm takes? This algorithm takes time of order of n. Order of n. How order of n? Because this loop runs n times. Okay, every time, for every element we will do the square. We can print the square also. It's a spelling mistake or something. Okay, it's returning, na? S. And then I can print the S. I have to run this again. And S is this list. That is the square of these numbers. So simply, I just want to tell you, this algorithm takes n steps, n iterations. It's a local function. You can give any name of this function. This is my user defined function. Def is a keyword to define a function, and you can give any name. Those who have issue in the Python, you don't know the Python basics, you can attend the next class. In the next class, I'll cover each and every basic of the Python. Okay. So simple things, I have taken only the simple program, and that is taking the order of n time. Similarly, I just want to search a item. Okay, or I'll just define a simple function, def double square. In place of square, I'm writing here the test function, and in this test function, I'm taking three variables, P, R, Q. Okay, and then inside this, I'm calculating a new number x is equal to p into r into q. And then I'll return x. Then how much time this function takes? This is a single iteration function. Test 2, 3, 4. I can run this. This is one iteration function. It takes only order of 1 time. Complexity for this is order of 1. And complexity for the last one is order of n. It depends on number of inputs. Just ensure how much time an algorithm is taking, how many steps it's taking to run. Okay? So here we can take another example also, like we can search an element in an array. So I just define a simple array L is equal to 10, 20, 30, 40, 50. And I'm going to do the linear search. Okay? How linear search works? You know linear search very well. In the linear search, we are simply searching an element. We are going one by one. Like here, x, I just want to find out. That is the 40. Okay? I just want to find out the 40. And for this, I need to write a code. Okay? So what code I will write here? I'll define a function def search, and inside the search I'll pass L, and then I'll pass the length of this list n, x. Length I'll define here. N is equal to length of L. Okay? And then inside this function, I need to write the code. Here I'm writing a loop simple. Don't worry about the Python code. I'll explain you each and everything. Don't worry. For I, here I just want to tell you about the how time complexities runs. How you will calculate the time complexity, or you can say bigger notation. So 0, n. And inside this, if L of I is equals to x, then we will return 1, otherwise we will return 1, otherwise we will return -1. Okay? And we will run this code, search L, n, x. Result, and result I'll print here. Okay, sorry. Why it's returning -1? One means item is present. If I'll write here 400, then it should return -1. What's happening here? We are traversing each and every element. It's searching for, first it will search 10, it will go to the 10 and it will compare 400 is equals to 10 or not. If not, it will go ahead, it will compare with 20 and then it will compare with 30, 40 and 50 till the length. If it is not present, then it will return -1. Okay? Anything you can return in place of -1, you can return 100. Anything, it's up to you. Like if this condition is fulfilled, then you can return a particular number. If it is equals to x, then we can return a number 1. It means this item is present inside this list. And if this condition never happens, this condition never becomes true, then it will come outside this loop and it will return 100. Like I value, initially I value is 0, and for 0, L of 0 this, then L of 1, L of 2, L of 3 and L of 4. Till L of 4 it will run this loop, and at any point of time, this if condition is true, it will return 1 and it will go outside the function. Otherwise, this loop is completed and it will return 100. You can write the break also, it's up to you. If it is true, then you can break it. And here you can send one variable. So at the case of that variable value, it is present, otherwise not present. You need to keep one more variable, because at the end we need to search out if result value is it's returning whatever it's returning, or any flag value, then you can use that. Yes, you can return the true false also. You can try it. It's a simple linear search, and even the program is available to our website also. You can go to the website, and in the lecture notes also we will provide you this link. Here you can see the linear search. What is the linear search? We will take an example of linear search and analyze it using the asymptotic notation. See, similarly, we are searching item by item. So here, now we will analyze worst case, best case and average case for this algorithm. Here the time also, we have mentioned here the time also, you can calculate the time also, but manually it is difficult to see the time, how much time an algorithm is taking. It's a very difficult, manually it's very difficult to analyze. So this is just for the understanding time module, but for this we need to analyze in the form of big O, and like it's a taking O of 1, O of n or average value. So basically, if we want to search particular element, that is the value is 30, and if 30 is present inside this, then we can say this value is present, otherwise it's not. So the best case, what is the best possible case? If we are lucky enough, and when we just want to search particular item, we just want to search the 10 and 10 at the first position, then it is the best case and it will take only the O of 1 time. Okay, and second thing is, when we are not lucky and when we are searching for an item and that item is not present there in complete list, if I'm searching for the 300 and 300 is not present here, then what will happen? It will take order of n. Okay, And for calculating the average case time, we need to calculate certain mathematical calculations. So we don't bother about the average case. It's for your examination purpose. You can calculate use the formulas. Otherwise, we don't need it. Okay. And next thing is, this is the simple, you can analyze these things. Okay. Similarly, we will do with the binary search also. Okay. Now we will understand the concept of binary search. How? Because linear search is very easy. Everybody knows about the linear search. Now we will come to the second type of search, that is the binary search. Okay. What is the binary search? In the binary search, like suppose we have the sorted list, and the sorted list have billions of numbers, and you want to find out a particular number. You don't want to go one by one. You don't want to do the billion of iterations, because it might be very time consuming. This list having 1000 elements, and you just want to search 999th position element. So for using the linear search, you have to go one by one. But in the binary search, we don't go one by one. Okay. This binary search is better approach if we want to search out for an element in the sorted list. Okay. So what we will do in the binary search, we will understand here. I'll tell you about this. How the binary search will work. There are the certain steps we have to follow in the binary search. Okay. In the binary search, first thing is, our assumption is sorted array. Array, or you can say a list. We should have a sorted array with us. Okay. Now what we will do here, I'll take an array 10, 20, 30, 8 elements. I have 8 elements in this list. So what I will do here, first thing, I'll divide my list into 2 parts. Or basically you can say, I just want to search x, and x value is 70. I just want to search 70. What I will do, first time, this is my list, and this list I'll divide into 2 parts. Mid part, mid of this list is this one. Mid, and this is first, and this is the last. Mid is first plus last divided by 2, always. So mid element, here the 0 indexing starts in the list 0, 1, 2, 3, 4, 5, 6 and 7. So 0 plus 7 divided by 2. It's a 3 point something. So you can say this element is my mid element. So this x we will compare with the middle element. X compare with middle. Let me write here. X compare with mid. Okay. If x matches with the middle element, then we will return this item. This is our best case. We will return this. If it is 70, it would be 70, then we will return it. This is the best case. Otherwise, what we will do? We will check our element is greater than the middle or less than the middle. Okay? We need to search in the first half or in the second half. We will find out like our element is less than the mid, or our element is x is less than mid, or x is greater than mid. If it is greater than mid, we will go in the second half. And again the same process we will perform here. In the second half, we will divide by 2 high and low. This is the first element and this is the last element. First plus last divide by 2. And mid element here is 60. Okay. Similarly, we will search out and at the end we will find the middle element. Or you can write here 0, 1, 2, 3. So what we will do? 0 plus 3 divide by 2. This is 1 point something. You can keep it 1 or you can keep it 2. It depends. Like this is the 2. So 70. 70 is the element and I'll compare this element with this. And this is the actual element. So within 2 iterations, I have got my element. And same thing, if I do with linear search, it will take the n iterations. This is not exactly 2, this is in term of the log n. Because every time we are dividing t, then t by 2, and then here t by 4, and t by 4, similarly t by 4. So this is a tree becoming a tree and height of this tree is log n. If you solve some recursion, then its height is log n. So that's why we are taking the complexity in the binary search is log n. Okay, so binary search is basically in the binary search, it's taking time in the terms of log. And always for the binary search, we need to consider the shorted array. And shorted array, it won't work. Okay. So let me go to the program part, how to write the program for this binary search. We will write the program for the binary search. Okay. Here, and then we will analyze it. You can see here, similarly the binary search, and for the binary search, the program we have written here, I'll write in the Google Colab also, but it will take time. I can explain from here and I can copy this code. From here. And I can copy this code here. And now I'll explain each and everything. This is the simple time module I have taken. Don't worry, you can remove this. You can remove this. You don't need it. Okay? And then we are defining a function binary search. High and low is first and last element. No, Ansari, it's in complexity of recursion is not always log n. We need to solve the equation. Here, if you solve the equation of this recursion that is becoming in the binary search tree, it will give you the value log n. Don't worry, we will see that also. Okay. Right now you can assume for the binary search it's taking time log n. I'll tell you that part also. Okay, so binary search, I'm writing a function for the binary search. What I need a list that I'm going to use for the searching, and the first element I need low, here I'm writing, and the last element I am writing here the high, and the x element which I just want to search. Okay, so in this list or in this array I just want to search out the x, and my array is sorted array. Okay, so what we will check first, this condition is for the complete, like high is always greater than low, means my array is having always at least one value or greater than one value. Like if I have only one value in the array, then high and low is equal. Starting point and ending point is always equal. Otherwise what happen? In array, if I have two items, then my low is 0 and high is 1. So it depends what is the low and what is the high, and high always greater than equals to low. This is the condition till we will run our another condition, inside conditions. So this is the this is for traversing the complete list. Okay, and then what we will do, mid is equal to high plus low divided by 2. If element is middle element, then what we will do, if L of mid equals to x, then we will return the mid element. Okay, if element is smaller than this mid element, then what we will write, we will smaller than the middle element. Okay, then we again apply return this binary search, recurs iteratively we will run, same function we will again call, and our low is low and high is mid minus 1. If first half, I am talking for the first half, low is as it is and high is mid minus 1. And for the second half, low is mid plus 1 and high is last element. Are you getting the things? Let me tell you one more time. So initially my low is 0 and my high is 7. Indexing starts from 0, 1, 2, 3, 4, 5, 6 and 7. Okay, and this mid is 0 plus 7 divided by 2. Okay, so it will calculate the mid element is 3. This is my mid element. Okay, now my array is divided into two parts. One is 10, 20 and 30, and this is the mid element, and second part is 50, 60, 70 and 80. And if element x is equal to 70, and here we have 40. So what we will check, first we will check if mid equals to x, then we will return this element, we will return true and this element is found. Otherwise we again call this binary search, and for this low is equal to mid plus 1 and high is equal to high. So what we will run? We will learn our array, and then low is mid plus 1 and high is h, and then x. And similarly, if I talk about this left one, here L is equal to L, low is equal to low, and high is equal to mid minus 1. So what the binary search calls? Binary search array, whatever the array I'm working over, and my low is as it is, and now my high is changed, mid minus 1, and then x. This is the binary search, and this is the binary search, and my initial binary search is array, comma, low, high, and x. Are you getting the things? So basically, this is my main function, and if my value is less than the mid, then I'll call this one, and if my value is greater than mid, x is greater than mid, then I'll call this one, and x is less than mid, then I'll search in this part. So if x is less than mid, I don't care about the second half, and if x is greater than mid, I don't care about the first half. Okay? Same process repeats till my high is upper condition. What is the upper condition? If high is greater than or equals to low. This is the outer condition. Okay? So this is the concept of binary search. And every time we are dividing into the half part. So obviously it will take the less time than the linear search. Yesterday I told you the example of dictionary also. Same thing we are doing in the dictionary. Binary search we are doing in the dictionary. They are ordered data. Yes, system only considers the indexing positions. It's indexing positions, and then by the indexing position, I just want to access this array. This is array, and I just want to access the element of this array, then array of index. Index is 0, either 1, either 2, like this. Okay? So this is the simple binary search, and now we can come back to our program. This is the simple function we have written, and this outer condition and mid we have taken. If always this returns, if L mid is equals to x, it return the value mid, otherwise it will go inside this else if condition, or otherwise it will go inside this condition. And fourth condition is element is not found. If we have traversed this complete if and it is not returning anything, then we can return -1. Okay? Now I can call this function L I am taking here. L is equal to 10, 20, 30, 40, 50, and X I am taking 30. Then I can call like this binary search L0 length L -1 X, and it will return inside the result. If result is not equals to -1, not equals to -1, then I can say element is present at particular index. Otherwise I can say element is not present. Yes, linear search is only for the binary search is only for the sorted elements. We will provide you lecture notes. You like you are doing the attendance, you have to write the attendance. For the attendance you have to write certain questions, answer over the LinkedIn and Facebook, and you need to write below this today's video session summary, today's video, below the today's video. So where you will get the lecture notes also, as well as with the questions. Okay, in the video description also you will get the lecture notes. Okay, now come back. Analysis of binary search, best case is we go 1, and if we are unlucky then we have to divide this array, and until we will get our element we need to divide again and again. So our worst case complexity can be log n. Okay, so our worst case, so what we get, we have seen linear search as well as binary search, and we have seen its complexities. Similarly, you can do the 2-3 questions, like you can find out the duplicate in the list. Question I'm writing here, write a program to find out duplicate of list, duplicate item in a list. Like what we will do, we can take the numbers is equal to, I can take a list like this, 3, 6, 5, and then 2, 4, 3, 6, 8, 3, 4. So here you can find out a particular item is duplicate or not. Like 3 is duplicate here, right? And 4 is also duplicate. I think 4 is not written. 5 is duplicate. 5 is duplicate, and 3 is duplicate, and 6 is also duplicate. So you need to find out the element, duplicate element in a list. So what we will do, we need to write 2 loops here. Okay, so complexity for this question, if you find complexity for this question, complexity would be n square. How to write the power, I don't know. Okay, n square. There would be 2 loops. First loop, you will traverse complete list, and then again you can start from the second element, second loop, and then you will match the element by element. So what the equation will happen here, if I talk about this, there would be equation like this, a into n square plus certain b. If we make a equation for the time, you can say loops run n square time, and we are avoiding the constant terms. What are the constant terms here? A and B. When we calculate the time complexity, we always avoid the constants, and we are taking care about the growing term. Here the growing term is n square. Why we keep only the fastest growing term? Why we avoiding the constraints? Let's understand this. I'll tell you one thing. Like what's happened here? Sorry. What's happened here? This simple program. N times this loop runs. But maybe this statement also takes some constant time. This statement also takes some constant time, but we are avoiding these constant times. We are taking only in the term of fastest growing term. Here's 2 things. 2 rules we are applying, like we making an equation of time. Like an plus b. If a program is taking order of n time, it means its equation of time is like this, an plus b. If your program is taking the time order of n square, then its equation would be like a of n square plus b, order of n square. Here we are writing two rules. First is we are keeping fastest growing term only. I am writing here the two rules. Fastest growing. Keep and I'm writing in the short now. Drop constants. Okay. How this happens? If we take n value is very large, like we have a function like this, 2n square plus 4n plus 10, something like this. Time is equal to. Okay. If n value is very large, like n value is 1000, then what will happen? 2 into 1000 square plus 4 into 1000 plus 10. Okay. And you can see this first term, 2 6 zeros plus 4000 plus 10. So in respect to this term, these two terms don't have as much weightage. And if n value is 10 to power 5, then obviously this term growing. So that's why we are keeping only the growing terms. Like we are taking 10 million. So in case of 10 million, this 4040 is very less value. Or like 10 million 10 in plus 10 million square into 2. 10 million square into 2 is bigger term than the second term. So basically in the big O, we are keeping only the fastest growing term. Okay. And in terms of binary search, like somebody is asking the question how we are getting the log n. I can tell you about the log n also. Like I'll create another file. How we are getting the log n? Basically our function is t of n, and every time we are dividing n by 2, t of n by 2. Similarly, t of n by 4 and t of n by 4. Okay. Now if I take kth iteration, you can say, I can write like this, k is equal to n divided by 2 to power k. In the first iteration 2 to power 1, then 2 to power 2, n divided by 2 to power 2, n divided by 2 to power 3, similarly n divided by 2 to power k. Right? Okay. And if I'll take like log of this, or suppose I'm assuming here the 1 is equal to n 2 to power k, and 2 to power k is equal to n, and then I can take the log both side. Log of n is equal to k log of n log of 2. It's not n. Okay, so finally k is equal to log of n, something like this. So hence the complexity of binary search is log n. We will solve the recursion like this. Okay, so simply we can calculate the equation complexity for an algorithm. Okay, every time it's taking certain n, and inside the loop how many statements we have, we will multiply with the n, and if these are the two loop inside the loop, then we will constant term we will multiply with the n square. Okay, so equations we will do like this. Rohit is asking a question, what is the asymptotic notation? Rohit, I have told you the definition of asymptotic notation. In the asymptotic notation, we measure the time taken by the algorithm in a form of some mathematical formula or with respect to increasing the input value. Okay? So you can see the, you can get the values like this for the asymptotic notations. Now come back to this. These things we know. Binary search we have done. The program part also we have done. Okay. Now come back to the asymptotic notation. There are the different type of asymptotic notations. Okay. First is big O notation. Similarly, we have omega notation, theta notation, and little o notation. Maybe you have heard about these notations. So big O notation is, it represents the upper bound of the running time. Generally, for the worst case complexity, we always consider the big O notation. Okay? So here you can see the equation. This is like I can tell you. This is my function fn, and this is the second one is gn. Gn is upper bound of this at a certain value of n. This is n input and this is the time. And this value of n is n naught. So we can say if n value is greater than certain n naught, we can say f of n is less than equals to big O of g of n. Something equation we are writing like this. And there are the certain, all these values, this n is greater, positive number, n naught is positive number. So it is upper bound. And if I talk about the lower bound, then it would be like this. I can change the color. This is my g of n, and this is my f of n, and this is n naught. So bigger notation is, first one is bigger notation. And second one is what? Lower bound. Do you know? This is the bigger notation or theta notation. Lower bound, sorry, we do the lower bound in the omega notation. Bigger notation always the upper bound, and omega notation always the lower bound. And if you want to calculate the both bounds, then we use the theta notation. Generally theta for the average cases. So for the best cases, we use omega notation, and for the worst cases, we use bigger notations. Okay? I'll give you some time. You guys can ask me the question. Till now, what I have covered, little bit about the notations. I'm not going inside the math about the notations. Simple analysis of algorithm, how to calculate the complexity of algorithm, and what is the performance measure, what are the asymptotic notations. You can ask the question regarding that. I'm getting certain questions also. Let me read that questions, okay? So first question is, Pratyush has written a question. Best case is that in which element is at mid position, in which we need not to use recursive call as well. Yes, Pratyush, for the binary search, best case is when our element is at the mid position, you will get at the first time. If the first element is the searched element, then it takes more time. Yes, in the binary search, if you are searching for the first element, if an element is present at the first position in a list and you are going to search with the help of binary search, then it will take more time. Okay? Little o we don't use h much. You can read out the theory part here, how the little o works. So we don't care about the little o. It's for non-negative functions. And asymptotic notations. Sanidhya Kumar is asking a question. Asymptotic notations. I have repeated this definition so many times. Right? You guys should know that definition. And I'll ask that question in your attendance remark. What is the asymptotic notations? Performance measure, you should know there is the different, for the performance analysis, there are the different measures: correctness, simplicity, optimality, readability, time complexity, and space complexity. We have only covered the time complexity part. Similarly, we can calculate the space complexity also. I'll tell you that part also. Like correctness is simply, we are checking the correctness for the algorithm, and simplicity and optimal and readability. These are the simple things you can identify easily from an algorithm, from a program. But when we go towards the space complexity or time complexity, it will take little bit time. Space complexity is how much space a particular program takes. Particular program variables takes the how much space. Space complexity is the amount of space required to solve an algorithm. A memory space, basically I am talking about the memory space. Okay? So space complexity of a computer program is amount of memory space required to solve a problem as a function of size of input. We always talk about, in the asymptotic notation, we relatively talk about the size of the input. Okay? So if I talk about the space complexity, we will write the space complexity in the form of like this: sp is equal to c plus sv of I. C here is a fixed value, and this sv of I, which is independent of, C is independent of input and output, and this sp of I is the space that is occupied by the variables. It depends how many variables we are using. So how much memory we are occupying in a particular program, that is called the space complexity. Okay. There are the certain rules, certain components of space complexity. 3 components you can consider basically: instruction or code space. Like line by line, we have written a code, we have written a program for linear search. That program contains 5-6 lines. So where we are saving this program instruction, where we are saving the instruction, how much space this is taking, the space holds the collected version of the program instructions. Second space holds all the static data, like whatever the variables we are using, whatever the constant we are using, and dynamic data we are using, how much space they are taking. Okay. And environment stack space. This space is used to store the return address for the functions so that the execution can begin again where they left earlier, and it may also be used for the parameters. Here we have taken a simple example also, a simple program, a simple function call, and you can see the different type of parameters we need for the space calculation. How much parameters we need, a return address we need, total recursive call, how much we need. These are the space needed for a program. So this is the space complexity. I think you should clear with the space complexity now. Now come back to the time complexity. Time complexity, we have covered different aspects of the time complexity. Again, we will re-revise this time complexity. Time complexity is amount of time taken by the algorithm to execute a task. Time complexity of a program is amount of time taken to solve a problem or function of a size of as an input. Like as far as your input is grows, how much time it can take. So with respect to input size, we always calculate the time. It's not basically in the seconds the time. We are calculating the time in the form of variables like order of n square, order of n cubic. Or like this, we calculate the time. And different components we consider for the time also. And measures of time complexity, I already told you: average case, worst case, best case. And these things are depends with the size of input. Okay. So this is the important article you guys know. And second important article is about this notations. And one article is about linear search and binary search. These 3 articles you should read carefully. Each and every step you should know about these articles. Then only you will get to know what is the asymptotic notation. And you know guys, for the data structures, if you know the asymptotic notation, then only you can pick the right algorithm. Otherwise, it won't possible for you to pick the right algorithm. Now, one last question I have to ask you: does asymptotic analysis always work? Let me write here. Always works. Can you tell me some examples? Like, what are the exception cases where the asymptotic notations are not working? Meanwhile, I got certain questions also. What is the asymptotic notation? Sanida, I have already told you, we have only the asymptotic notation. There is no asymptotic notation. We are using the asymptotic notations. We are not using the asymptotic notations in the data structures. Okay, I got an answer from Pawan. In some cases, we cannot predict only using the asymptotic notations. Yes, right. Tell me a little bit in detail. What type of cases? What type of cases we cannot predict in asymptotic notations? I just want to ask you this question only. Real-time calculations. Okay. And let me tell you the one example. Like here we are taking care about only the growing term. We are avoiding the constants. Like there may be an algorithm that is in the order of log, or you can say 10,000 n to power 4, and one is the 10 to power 6 into n to power 4. There is two algorithms. Okay, these two algorithms are having same order of n to power 4 or n to power 4. But you can see here the constant is different. Both algorithms have same asymptotic notation. Order, not a notation, asymptotic order. Same asymptotic order value we have. We cannot say which one is the better, because we are ignoring the constants. One thing. Second thing, it might be possible like we never get the larger value of input. Like we are talking always about the large value of input. What happens sometime, like we are using two algorithms and we got the asymptotic order for we are considering case when we get the large value of input, but we never get the large value of input, then it is useless. Maybe we discarded the good algorithm that is for the less value of input. Okay, so it might be possible that the larger input are never given to your software. So algorithm which we are using, maybe that algorithm is slower algorithm. Some other algorithm that is the faster algorithm. For less input, algo 1 is fast and algo 2 is fast for the more input. So you never give the large input. So you are avoiding this case. You are avoiding the constants. Okay? So it's a little bit things we are avoiding, but in the 99% chances, asymptotic notations always gives you the good algorithm. On the basis of asymptotic notation, we are always picking the good algorithm. 99% time. It's not always. Okay? So in certain conditions where we are avoiding the constants and where we are not taking the large input, that two possible conditions. Okay guys, I think this is enough for today. Okay, We have covered asymptotic notations almost in all the way. You guys just revise these 3 articles and you write your answers below the questions we will provide you over the LinkedIn and or the Facebook, and just write the session summary below the session so that the things will get brush up to you. Pawan is asking a question. Performance of the same algorithm changes when run on different machine, right? Yes, Pawan, that's the point I initially raised. Algorithm performance depends on the hardware also. But always, I have taken an example where linear search we are running over the fast computer and binary search we are running over the slow computer. But when we increase the input value, your slower machine will give you the fast output depending on the input. Always, if asymptotically it have the less value, then it is always execute fast. Doesn't matter of the machine. Okay? So these are the things we have concluded today. Asymptotic notations, average case, best case and worst case. We have studied linear search and binary search. Okay guys, thank you so much and bye bye. See you tomorrow.